Welcome. In this video I'll discuss the chodura sheath, and this is a magnetized sheath where there's a magnetic field, and in particular where the magnetic field is at an angle to the wall. And this is the case in most fusion experiments, most laboratory plasmas. The magnetic field is at some kind of shallow angle to the wall, and this means that the orbits of the ions are important in the boundary conditions at the edge. And so we'll look at the so-called magnetized pre-sheath. So this is a layer which is a few Lama orbits wide in front of the wall, where the ion orbits intersect with the wall. There's an analysis originally by Chodura, and then in a different way by Riemann, which shows that essentially the boundary condition becomes the parallel ion flow, becomes the sound speed. And so actually the boundary, although it becomes much more complicated to analyze, the boundary condition at the entrance to the sheath is essentially the same as the Bohm sheath perpendicular to the wall, which is quite nice. It makes things much easier. So this is a justification why you can use essentially the Bohm sheath criterion with a perpendicular magnetic field, is because even when you include the angle, the result stays the same. And there are some useful papers. This Stankovic paper is kind of a review. This is quite nice. It reviews this Riemann paper and expands on the method it uses, and I'm basically following this method here. And then this original Chodura paper, which analysed the sheath in a different way, gets the same result. Okay, so here we'll first review what a normal sheath looks like. So if you have a sheath which is either unmagnetized or the same result when you have a magnetic field perpendicular to the wall. So you have a wall like this. You have ions which are flowing into the wall and then are accelerated to higher speed by electric field. And then this is in a region here. You have the sheath in this region here, which is of the order of a few Debye lengths across. So this width here is like Debye length, or a few Debye lengths. And then we have electrons, which also like this. So electrons are pulled into the sheath and then reflected. So these are reflected back by the electric field. Okay, so in a magnetized plasma, we have essentially a wall, and then to minimize the heat loads on the wall, typically the magnetic field, which I'll draw here, is at some kind of angle to the wall, and this angle is usually called alpha. And alpha may be roughly like 1 to 3 degrees, for example. So it's a small angle, and the aim is just to spread the heat load. So you have a high heat flux coming along the field, and to spread it over a wide area, the angle between the field and the wall is made small. And so this, just by geometry, spreads out the heat. It can't be made too small because the wall is made out of individual blocks, or it has surface irregularities. So it's not a perfectly flat wall. But this means that the electrons, for example, are spiraling with a very small orbit. So the electrons are essentially stuck on the field line. The ions, I'll draw. The ions have a much larger Lama orbit. As the ions essentially come in like this. And then what we'll see is there's a region near the wall, which is a few Lama radii wide. So this is of order the ion Lama radius. And in this region there's an electric field which accelerates the ions towards the wall. And it's a quasi-neutral region, but it balances the boundary condition along the field lines to the Bohm boundary condition, because there's still, in this region here, there's still a very narrow Bohm sheath here. So here you have the standard Bohm sheath. Which is this sheath here. So this is Bohm. So essentially the unmagnetized case, or case with magnetic field perpendicular to the wall. And here you have the sound speed. So ions are going the sound speed perpendicular to the wall. What we'll see here is that the boundary condition we'll end up with is that the parallel speed for the ions is the sound speed goes to the sound speed at the entrance to this magnetized pre-sheath. And here, at this point here, V perpendicular to the wall goes to the sound speed. And so there's an electric field in this region here, which accelerates the ions to match the bone. And so this region here is called the magnetized pre-sheath. So there are some useful facts about it. So first, it's a quasi-neutral. So the electron and ion densities are similar in this region here, unlike the sheath, the bone sheath, which is not quasi-neutral. So there's a higher ion density than electron. And this sheath is quasi-neutral. So Ne is roughly Ni. It's much larger than the bone sheath because typically rho I is much bigger than lambda d. So this might be micrometers, whereas this is millimeters or 0.1 millimeters, for example. So these are usually pretty big, but much larger than the Debye length. Saying the boundary condition you end up with is on the parallel heat flux and the parallel ion speed, and is as if there was a bone sheath perpendicular to the field line. So the way we're going to solve this is to have end up with essentially two conditions. So one is the usual bone condition here at the bone sheath entrance, and that's that the perpendicular velocity of the ions is sound speed. And then there's going to be a second condition on the entrance to the magnetized pre-sheath, and that's going to be the parallel speed is going to the sound speed. So in the magnetized sheath, we need to take into account the ion orbits. In the Debye sheath, because this is so much larger than the Debye length, you can just ignore the ion orbits inside the Debye sheath. Inside this bone sort of lengths of a few Debye lengths. So inside this bone sheath region, you can ignore the ion orbits. In this region here, which is much larger, the order of the ion alarm radius, you have to take into account the full ion orbits. And there's one last thing, is that if this angle alpha becomes very small, so imagine in the case where the field line was just horizontal, so parallel to the wall, then the electrons can't get to the wall, whereas the ions can. If the angle is very small, then the ions can still hit the wall before the electrons do, and then you have a reversal of the usual situation. So in most sheaths, the electrons hit the wall first, and so there's an electric field pointed towards the wall. If the ions hit the wall first, then there'll be electric field pointed away from the wall, and there's a critical small angle. And this occurs when there's the ratio of the ion thermal speed divided by the electron, so the thermal speed of the electrons. If the alpha is comparable to this ratio, then the ions can reach the wall the first, and this is roughly like the square root of the electron mass over ion mass, which is for deuterium is about 1/60. And so if alpha is smaller than this, then the sheath behavior can change quite significantly. Okay, so now we're going to try and analyze this situation. So we're going to solve essentially fluid equations inside this magnetized pre-sheath, inside this region here. So we're going to assume it's quasi-neutral, so Ni equals Ne, and we're going to solve essentially for the fluid equations in that region. So this is the analysis method that Riemann used, but gets the same result as the chodura method. So it's quasi-neutral, so assume so Ni is Ne. Assume the same Boltzmann response for the electrons, the same as the bone sheath, and then we have the continuity equations for the ions. So we have the divergence of Ni times U, where U is the ion flow speed, or the fluid flow, and this is the ion density. So that divergence is 0, so it's steady state. And then we also have the momentum equation, so the ion mass, Mi, also drops the time dependent part, and then we just have the forces due to the electric fields, magnetic field, and the pressure. And here, because it's steady state, the electric field is just minus ground phi. So then we can make some more simplifications and choose a coordinate system. So we're going to define, so this is the wall. We're going to define this is the z direction is downwards. We define this as the x direction is horizontal. We have the magnetic field, which is this way, so this is the b direction, which we can label parallel direction. We have an E field, which is downwards, so we're going to assume the standard sheath. So we have an electric field in Z, and this means you have an E cross B velocity as well. So we have E cross B, which is into the page. And then we're assuming that the thickness of the wall is small compared to, so the thickness of the pre-sheath is small compared to any variation in the wall. So there's no variation in the x direction, so only variation in the z direction. So I take the z component of the momentum equation, and then because we just use this Ez is just minus d phi by dz. And this pressure term here, this is a bit more tricky. First we take the iron pressure. This is E times Ti times N, where N is the density. We're assuming that N, so N is just Ne is Ni, so all cos neutral. And then this part here is just E times Ti times the log of, or the derivative of the log. So this is Eti d by dz of log n. And then we substitute in, for log n, we substitute in the Boltzmann relation. So take log of this, and just have that log n is the log of n naught plus phi over T E. And so that substitutes into there, and then that of course is a constant n naught, and so that just turns into a derivative of phi over T. And so we can write this whole thing as, we here have just rearranged it a bit, so we have the E term here turns into this phi term here, and the pressure term here just turns into this part here. And so again, Ti is assumed constant and Te is assumed constant. So Ti and Te are constant. Again, the sheath is assumed thin enough that any temperature gradients are small, and so the ion electron temperatures are constant, at least across the sheath. Okay, so then this we can just rearrange a little bit. So then we need to work out what this part is here. So we need an expression for phi in order to simplify this. And the easiest way of getting this is from the continuity equation. So we have the divergence of n times u is 0. So we have the z component, we just have the d by dz of n times uz equals 0. Again, putting in n from here, from the Boltzmann relation. So therefore we have the d by dz of n naught e to the phi over t Te times uz equals 0. And so just integrate this up trivially, and it just says that n naught e to the phi over Te uz is a constant. And then we can choose our constant by saying that defining phi equals 0 when we're at the entrance of the Debye sheath, so at the Bohm condition. And so we define at the entrance of the Debye sheath phi equals 0, and so this e to the phi becomes 1. And then at the Debye sheath n is equal to n0, and the so U is equal to the sound speed. So the ions are going sound speed into the sheath, and so this is just N0 times CS, and so because at that point this is equal to 1, and so therefore we can just rearrange this whole thing, because the N0's cancel. We just end up with, so it's the phi is equal to minus, because we flip this upside down, so it's TE from here, then the log, so we take log of both sides, so you have a CS divided by UZ. We turn this upside down, so I have a minus sign, so phi is equal to minus TE times log of UZ over sound speed. And this we can then put back into, so this term here, we go back into here. And so then we end up with a d by dz of this log term here. So putting this term for phi back into this term here, we can write out this equation for the z component of the ion velocity. And of course now we have something in terms of duz by dz on both sides. So this coming from the original momentum equation, this coming from the potential. We can just combine them together and we get an expression. So this is the expression for the velocity in the z direction, so the perpendicular to the wall. I'm going to come back to use this very shortly. So it's just related the rate of change of the velocity in z to the velocity in perpendicular to the page, so in the E cross B direction. So we need to know what this term is, the E cross B, and so we can write down this component. This is much easier to write down, we just have this. So we can combine all these different equations for the velocities together, or equivalently you can write down something for the just the kinetic energy of the ions and the total energy of the ions, and you get an equation like this. So for the energy, you get an equation involving all the different components, so essentially v squared, so the velocity squared of the plasma, which is just a combination of all the different components. So that's essentially the kinetic energy of the ions, and this is equal to the energy that comes in. So this is essentially the potential. So the potential energy of the ions when they come into the magnetized presheath, plus then the parallel flow of the ions. So assume they have some parallel flow as well. So this is like the V parallel or U parallel at the entrance to the magnetized presheath. And then you can combine all these together and you get an equation like this. So an equation here on the left is some function of uz, which depends on the ion line radius, so rho I. If you remember here, this is just related to the sound speed divided by the cyclotron frequency. Well, the cyclotron frequency is just EB over MI. So this gives you a line radius, ion line radius effect. This whole thing we just call some function f. So some function f of uz. This is the parallel VS all squared. So it's just the V parallel all squared. So it's an expression on the right hand side involves a whole bunch of different terms from the Vx term, from the this term here, so it comes straight here, from the E cross B velocity, from the Ux terms. Here alpha is this angle of the field line, and delta here, so this delta is just defined as tan, essentially tan of alpha. And it's just the ratio of magnetic field strengths, so Bz over Bx. So then what we're going to do is take this left-hand part of the equation, we'll take this whole thing here, so to find this as f, then take square root of this equation, and we can write this as, so essentially ignoring all this stuff here on the right hand side, so whatever this is on the right, we just call it f, and we can simplify this equation and just solve this part here. We can just write down, so here I've just taken the square root of this equation, so you end up with a square root of f, and then divided through by a square root of f, so you get f to the minus a half here. and then just a 1 on the right hand side. Then we solve this by separation of variables. So take this, essentially take this dz over to here, and then everything here is a function of uz. So here's the function of uz. Cs is a constant, and so we integrate by separation of variables. And so the right hand side here, so integral of 1 dz just becomes z plus a constant, and we can divide through by rho I. And so this right hand side here just becomes essentially z divided by rho I. And then on this side, we end up with, depending on the sign here, depends on which boundary condition you set, but essentially it's got a minus sign because I'm going to the Debye sheath rather than from the Debye sheath outwards. So this is the Debye sheath entrance, so the BOEM where uz is equal to sound speed. So saying that into the wall, or at least into the BOEM sheath, the ions are going perpendicular at sound speed, and so that becomes this boundary condition at the Debye sheath. And this is the boundary condition at the or the boundary at the magnetized sheath entrance. So then the proof, essentially you don't need to solve this. So this f here inside this equation is this right hand side function here. So what we then do is we solve for the solutions close to the magnetized pre-sheath entrance, where uz is equal to uz0. So at the magnetized pre-sheath entrance, uz is uz0. And we're going to expand, Taylor expand. So we're going to Taylor expand around uz. It's around uz0. It turns out that the first two terms in that expansion are 0. So f of uz0 is 0, and also f prime of uz0 is also 0. The second term is the important one. So this is the second term in the Taylor expansion. So you get this multiplied by by uz or uz squared. So if this is negative, for example, then this would be negative, and then we'd have a square root of a negative value. So this must be bigger than or equal to 0. If the square root of f is real, which of course, because this whole expression, all these terms here are real, and so if z is just a coordinate, so that must be real, and so this must be real as well, and so this must be larger than 0, and for this to be larger than 0, we must have that the parallel flow speed is bigger than the sound speed. Or bigger than or equal to the sound speed. I'm going to call the chodura condition, or BOEM chodura, or BOEM chodura Riemann condition, some combination of them. But you see it's essentially the same condition as the BOEM, it's just now it's in the parallel direction rather than perpendicular to the wall. But the analysis is quite a bit more complicated. I hope that's given at least an idea of how the derivation works. If you look through the papers, you'll see there's in some ways a little more detail, but in otherwise less detail. I tried to fill in some of the steps that are missing in the papers. So hopefully you can follow this through and see for yourself how this works.